Hey, algebra. All right. We're going to jump into 7.4 radical expressions. Yes, they are radical. One objective for the day: simplify radical expressions by using the product rule and the quotient rules of square roots. Um, so, you guys, today I broke this up into two parts. We're going to extend this lesson over 2 days because it is very involved and there's a lot of information here. I'm only going over the first three examples for this one. Let's get into it. This is like probably one of the most important slides here because this is what we're going to be dealing with for the full lesson, and that is we must, when we are dealing with radicals, we're going to be asked to simplify them. In order to simplify them, three important conditions must exist. Okay, so number one, we can have no radicands. That's like the thing that's inside the radical. In the particular example that I have here, to the right of this, we see that it's the square root of 4. 4 would be the example of the radicand. So we can have no radicands that have perfect square factors other than 1. So I can't leave something like the square root of 4 in that form, because when I take the square root of 4, that's a perfect square, right? Because 2 times 2 gives me that 4. I can reduce that to 2. So I would want to write it as 2, not as the square root of 4. Okay. Number 2, no radicands contain fractions. All right, so I can't have like the square root of 1 over 2. I can have the square root of 1 over 2, but not the square root of 1 over 2 like this. Okay, so notice the difference there. And then finally, I cannot have a fraction in which I have a radical in the denominator. This goes back to a convention that we did a long time ago in math before we had nice calculators to deal with these kind of things. But today still, even through pre-calculus, calculus, we don't want any radicals in the denominator. And the main reason for this is that's a really ugly number, right? It's a decimal that goes on forever. So I don't want to be dividing things by decimals that go on forever. So we get rid of the radical in the denominator, and I'll teach you how to do that today. Okay, so the product property of square roots essentially says that if I have the square root of anything, like let's just say I have the square root of 3, and then I also am multiplying this by the square root of, let's just say 6. I don't know. What the product property of square roots says is, if I have something like the square root of 3 times the square root of 6, I can say that that's the same thing as the square root of 18. Okay, so you can multiply those two things together and it'll be the same as the square root of the products there of 18. All right, so that's what it's saying. What this also means is I can break it apart. Okay, so notice the examples that they give us. The square root of 4 times 9 is equal to the square root of 36. All right, I could break that up into two pieces and I could say, okay, that's the same thing as the square root of 4 times the square root of 9, which are nice, this was nice too, this gave me 6, but these are also nice perfect squares. That's the same thing as 2 times 2. That's the same thing as 3 times 3, so those are called perfect squares. The square root of 4 is 2. The square root of 9 is 3. 2 times 3 is 6. So it's just kind of proving that that this whole property works. Okay, so let's simplify square roots for a little bit here. So you might want to write these perfect squares down as you're learning this. A lot of my students will write these down because they're not super familiar or used to these. Other students are, but we know that where these perfect squares come from, I hope. So let me just give you a little visual for the first one here. If I have a square and I divide it up into individual 1 by 1 pieces, okay, notice here that there's 4 pieces, right? And if I break it up into even pieces, then it's a 2 by 2 square. So the perfect square of 4 is 2, right? So 2 times 2 gives me the perfect square 4. 3 times 3 gives me the perfect square 9. 4 times 4 gives me the perfect square 16, etc. It goes on and on and on. So to simplify square roots, we have to take out any perfect square that we see by breaking the root up. Okay, so this is not always easy to see. If I have the square root of 80, for instance, one of the things we're going to be doing is we're going to be seeing, okay, are there any perfect squares inside of here that go into this evenly? And right off the bat, I know that 4 does, right? So 4 would go in evenly, but I always look for the biggest one. And in this case, as you can see from the example here, 16 goes into 80. And 16 is also a perfect square. So always take out the biggest one that you can find. So since 16 goes into 80, I can rewrite the square root of 80 as the square root of 16 times the square root of 5. Okay, and then now I have this piece or this perfect square that's here that I can actually take out, and that's what we're going to be doing a lot of today. So that square root of 16 is simply 4. So I have 4 root 5, and I'm done. Okay, so you're always looking for that. If you leave it on your test as the square root of 80, it's not going to be fully correct because we're trying to simplify that thing. Is to take the perfect squares out. So here, let's try some more examples of this. We have the square root of 54. Think about which of these perfect squares, 4, 9, 16, 25, what number goes into 54 evenly, if any of them. So you might want to start at 4 if you're unfamiliar with this. Start at 4, see if 4 goes in. If it does, you could break it apart. In this case, I know 4 does not go in. So when I go to 9, 9 goes in. And if you're not super familiar with your times tables, it's time to start really getting familiar with those. But you might be using a calculator a little bit, which is okay. So this is the same thing as the square root of 9 because 9 goes in and it goes in 6 times. So 9 times 6 gives me 54. So that's an okay statement to say that that's the same thing as the square root of 9 times the square root of 6. The square root of 9 is 3. So the reason I did this was to get that whole number 3 out of there because that's a perfect square. So it's 3 root 6. And I always like to check this again. Okay, so I say, okay, well, does 4 go into that evenly? No, because, the next thing that 4 goes into evenly would be 8. So that's the last number that would work, 6 in that case. So I can leave it like that. The 6 stays in the radical, the 3 comes out, and I'm done. Hey, one way to check your answers on this, by the way, put this in your calculator. Put 3 times the square root of 6 in your calculator. You should get some kind of decimal. And then put the square root of 54 in your calculator, and you should get the same decimal. Okay, so when you want to check your answers, it's as easy as that, making sure that the simplified version is the same as the original. All right, so a couple more here. We have the square root of 180. So again, I know that 9 goes into that, right? So I'm going to break this up right away. This is the square root of 9, because I know that 9 goes into 18. And so the other one would be, so catch this, the other one would be 20 here. Okay, there's a reason that I chose 9 and 20, even though there's another perfect square that works here. I want to show you something. So if that's the one that you chose, then you'd be left with 3 root 20. Now, many people would be tempted to stop here, but you always have to look here. Do I have more perfect squares inside of that? And the answer to that is yes, I do. This can be written as the square root of 4, right? Because 4 is one of our perfect squares, times the square root of 5. So now I have 3 times the square root of 4 times the square root of 5. The square root of 4 can be simplified to 2. So now I have 3 times 2 times the square root of 5. 3 times 2 can be simplified, that's just 6. So I have 6 root 5. And again, I would encourage you, put that in your calculator, see what that equals, put the square root of 180 in your calculator, see what that equals, and then make sure that we did that right. Okay, so that's the square root of 180, example 1b. Next, you guys, we're going to get into multiplying square roots. we've kind of already talked about this, so I don't know why I made this a separate slide, but so the square root of 2 times the square root of 14 equals the square root of 28. Are there any perfect squares that are in this guy? And the answer is yes. 4 goes in, right? 4 is a perfect square that would go into that. 4 goes into 28 7 times. This is the same thing as the square root of 4 times the square root of 7. Square root of 4 is just 2, so it's 2 root 7. Okay, so when you multiply those square roots out, you also have to make sure that you check for perfect squares in the solution to that thing. So here we have the square root of 5 times the square root of 10. All right, well, that's the square root of 50. I see right now, so thinking about my perfect square, so 4 does not go in, right? That's 2 squared. Let's try 3 squared, that's 9. That doesn't go in, evenly at least. Let's try 4 squared, I get 16. That doesn't go in evenly. 5 squared gives me 25, and that does go into 50 evenly, so I'm going to use that. This is the same thing as the square root of 25 times the square root of 2. 25 times 2 gives me 50, right? So that's okay. Square root of 25 is 5, so I have 5 root 2. Okay, that's the simplified form. Example 2b, give this one a shot, you guys. So this would be 48, right? Square root of 48. I know that 2 squared, 4 goes into that. Okay, so I might start with that, but then I also, since it's even, I like to check the next even root. So we have 4, 9, we have 16. If 4 goes in, I like to also check to see if 16 goes in. And in this case, it does, I believe. So 16 times 3 goes in. Okay, so this is the square root of 16 times the square root of 3. By the way, if you did not see that and you chose 4, that's okay. Because what you would get is you would get the square root of 4 times the square root of 12. Okay, and I'll show you how that one works in a second. So square root of 16 is 4. Square root of 3 cannot be simplified. I'm done. How can I get that same thing over here in red? Well, this becomes 2 root 12. But then 12 has another 4 in it, right? So I can write that as the square root of 4, square root of 3. So that becomes 2 times 2, because that 2 comes down. This is a 2 times square root of 3, which is 4 root 3. Okay, so that just involves a couple extra steps because we didn't take the biggest square out of there. Notice what happens when you plug a negative 3 into the following expression. Okay, so now we're considering an expression where we have an x instead of a number that we're plugging in here. When you plug a negative 3 into the square root of x squared, okay, what you end up with is the square root of negative 3 squared, which is negative 3 squared is just 9, so it's the square root of 9, which is just 3. So the special rule here is this that I want you to see. If you plug a negative into this thing, you'll get a positive out. Okay. If you have a negative, well, let me say it this way because I think it'll be more clear here. That with all even exponents will make a perfect square, just like we saw here. But notice what happens if you had something like the square root of x to the third and you plugged a negative 3 in there. Well, negative 3 to the third, if I have negative 3 to the third, that is negative 27, and you cannot take the square root of a negative number. Okay, so we know that that just does not work. So all even exponents are perfect squares. So if you plug an even and negative in, you get the absolute value of x out, right? So that's what this was. This was the absolute value of what I plugged in. That's because you're taking that same thing, negative 3, and you're multiplying it by negative 3, and you're always going to get a positive, right? So it's always going to be the absolute value of what you plugged in. All perfect squares must be taken out of the radicand. So number 1, all even exponents are perfect squares. Okay, so if I have the square root of x squared, I'll get the absolute value of x out. Number 2, all perfect squares must be taken out of the radicand. So if I have x to the third, I can take the even square root of x squared, I could take that out, so I can write that as two separate pieces. So what I did was I'm just breaking that 3 up, right? I'm breaking that 3 up into pieces because I know that if I have something like x times x times x, and I'm taking the square root of this, the square root undoes essentially 2 of these. Okay, we know that we know from past math that the square root of x is the opposite of because this is equal to x to a half, it's the opposite of x squared, right? So if I take the square root of x squared, these cancel and I'm left with x on the outside, and since this is an odd exponent on the inside, I leave it in radical form. So all the evens come out, all the odds stay behind. So you end up with a lot of times if you start with an odd, you'll end up with just a solo variable in the radicand. Anyway, whenever I pull something out, if I go from even to odd, I must use a absolute value sign, which I will get to. Number 3, taking the square root of an exponent is the same as dividing the exponent by 2. Okay, that is a very, very, very important idea. When I take the square root of of something like, so let's do this one here. If I take the square root of x to the 4th, that square root undoes 2. So you just divide 4 by 2. And what I'm left with is x squared. So it undoes 2 of them, right? So I have the square root of x to the 8th power. I essentially divide the exponent by 2. So this is equal to x to the 4th. Now, the final piece here, and I know this is a lot to take in at once, is for expressions where the exponent of the variable inside a radicand is even, and you get a simplified odd, you must use an absolute value sign because of number 1, basically this rule that we talked about. If I plug a negative number into that, right, I don't know, it could be the negative or the positive, so I'm always, if I go from even to odd, if I plug something into this odd function, an odd exponent would give me could possibly give me a negative answer, but in my original, I couldn't have a negative answer. When you simplify something, you have to get the same answer when you plug something in. So whenever I go from an even, like x to the 6th, and I divide that by 2, I get x to the 3rd. If I go from even exponent to odd, I have to use an absolute value bar to show that you can only plug even numbers into that. Okay. So those are our rules. I know that that's a lot. Make sure you get those into your notes, okay, because those are going to be very important. So let's do example 3 now. So for example 3, I don't know why I did this out already, but here we go. We're looking at this guy. I'll do it again over here. So 90, we're going to break each of these pieces up into their perfect squares. I guess I can use what I did here. Okay, so 90. 90 can be broken up into the square root of 9, which is a perfect square, times the square root of 10. X to the 3rd, I need to take all my evens out of that. So I have x squared, that's the largest even in x to the 3rd, times the square root of x. Okay, so just to be clear, the square root of x squared times the square root of x is equal to the square root of x to the 3rd. I broke it up into these two pieces so that I can simplify parts of that out. Okay, y to the 4th, it's already even, so I'm leaving it as y to the 4th. Z to the 5th, I'm going to take the largest even one out, which is z to the 4th, times z. Okay, so now when I simplify this next round here, square root of 9 is 3. Square root of 10 cannot be simplified. The square root of x squared is just x. I leave this in the radical, the x. The square root of y to the 4th is just y squared. And then what else do we have here? We have the square root of z to the 4th becoming z squared. Take that, cut it in half, and then the square root of z is just square root of z. And what I'm left with is this guy. Everything that comes out, or that was pulled out, comes on the outside of the radical. Anything that was left in, like this, this, and this, stays inside the radical. All right, so let's look at this one. We have 32, so I know that 16 goes into that. Okay, so this is the square root of 16 times the square root of 2. r squared is even, so I'm going to just leave that as the square root of r squared. K to the fourth is even, so I'm going to leave that as the square root of k to the fourth. T to the fifth is not even, so I'm going to break that up. T to the fourth, that's the biggest even exponent in 5, and then multiply that by t. When I do this, the square root, now I'm going to simplify everything that I can. Okay, the square root of 16 is 4. Square root of 2 stays the same. Square root of r squared becomes r. Square root of k to the fourth becomes k squared. By the way, this has to be absolute valued because we went from even to odd. Then the square root of t to the fourth becomes t squared. And the square root of t just stays the square root of t. Now everything that it's pulled out stays out. So 4 k squared t squared square root of r. That takes care of all these. And then we're going to multiply that all by the root of 2t, and now this is simplified. Now, what I mean by simplified, you guys, is this has the exact same value as this. And it's written in a way where I can plug the same thing in for t, k, and r and get the same value out. But I pulled anything that was perfect outside of the radical. Okay, one more, you guys. Thanks for bearing with me on a long lesson. This is only half the lesson, by the way. So here we have the square root of 56. Okay, so I want you to practice this one, breaking it apart just like I did up here. Okay, but I'm going to also do it here. So, so for 56, I think that I think that 4 goes into 56. So if I take 4 into 56, I get 1, 16. I get 14, right? So I'm going to break this up into square root of 4 times the square root of 14. And then the square root of x just stays the same because it's odd. And then the square root of y to the 10th. I can't take any evens out of this one. This one is even, so I'm going to leave it alone. And then I have z to the 4th times z. Because that is odd, I want to break it into the biggest even. And then that one z left over. Okay, now when I do this, let's look at this. So we have the square root of 4, which is 2. Okay, so I'm just simplifying this. 2, square root of 14 can't be simplified further. And then I have the square root of x that can't be simplified. But then the square root of y to the 10th is just y to the 5th. Okay, so I'm done with that one. And the square root of z to the 4th is z squared. And then I still have the square root of z. Anything that is still inside the radicand stays in. So it's 14xz. Okay, dealt with those. And then on the outside I have 2y to the 5th z squared. The last thing I need to check is, did I go from an even exponent to an odd? And I did with the y, right? I started with y to the 10th, which is even, and I went to y to the 5th. So that's in absolute value bars, and I'm done. So whenever you go from even to odd, you got to make sure to remember those absolute values. Okay, guys, that's it for this lesson. So be patient with yourselves on this. I know this is a lot. We'll do some more of this in class, but hopefully this gives you enough to get a jump start. All right.